2018 Higher Level Leaving Cert Paper 2 Question 8 is a statistics question. Acme Confectionery makes cakes and chocolate bars. They have launched a new bar called Chocolate Crunch. The weights of these new bars are normally distributed with a mean of 4.64 grams and a standard deviation of 0.12 grams. A sample, very important, a sample of 10 bars is selected at random and the mean weight of the sample is found. So we're dealing with a sample here. So our Z score is going to be my test statistic X minus mu, which is my average, divided by, normally it's just standard deviation, but when we're dealing with a sample, it's standard deviation over the square root of the sample size. So if we just get let's get the Z score for each of these. We'll draw a diagram to begin with, just to see what we're dealing with here. So my average is in the middle, 4.64. I've one to the left. I'm going to just move it away to give myself room. And to the right, I have 4.7. So we're looking for what's in here. So what I need to do, I need to get the Z score for 4.7 and find out what the tail is. And I need to get the Z score for 4.6 and find out what the tail is. And take those two tails away from one, and we will have our probability of them falling between those two scores. So 4.6 is going to be negative because it's to the left of 4.64. So we 4.6 minus 4.64 divided by 0.12 divided by the square root of 10. And this one is 4.7 minus 4.64 divided by 0.12 over the square root of 10. Now in this case here, if you don't divide by the square root of 10, you're going to get an answer of a half, which would be in the middle. And just by doing your diagram, if you did do that, you could see, okay, I've done something wrong. So try and think about these questions as you're doing them and why you might use the square root of n on the bottom. It's when we're dealing with a sample within this inferential statistics type question. So this is just calculator use. This one's going to give me minus 1.054 minus 1.05. Just keep the same stuff in your calculator and change the values on the top. And this one gives us an answer of 1.581 or 1.58. So let's go to our Z score table and find what each of these give us. So there's no minus values, we're just dealing with the positive values. So 1.05 gives 8531, 0.8531, so 1469 would add up to 1, so that's what's in this tail over here. And 1.58 gives us 1.58. Just double check each time. It's not easy going across the columns and the rows. So many numbers. So 9429, 0.9429. And we would have to add 571 onto that. 571 to get to 1. So that's what's in this tail here. So in between. So adding these two tails together and taking them away from 1. So 1 minus 0.1469 plus 0.0571 is going to give me an answer of 0.796, 0.796, which is the equivalent of 79.6%. being in this blue shaded area in the middle of the diagram. Part 2 of this question is a population proportion question. And we can see that straight away. The company surveyed 400 people from the population of people who bought at least one chocolate bar. So we're taking a sample from the population. So this is your population proportion. And the formula for population proportion is to get what this gives us the margin of error of the population proportion that like the bar. So it's p hat times 1 minus p hat, or you can just use p. The square root of all that over n will give me the the margin of error for this proportion, which is 324 over 400, and if we divide that by 4, we're going to get 0.81. So 81% of people like the bar. So how confident are we within a 95% confidence interval? And if you look up 95, 0.95 in the Z-score table, you'll find a score of 1.96. It's a more accurate way than the empirical rule of 95% accuracy. This is just slightly more accurate than that. So we need to get this 1.96. So this p-hat is the population, and this is the square root, the population who, or the success of it, the 1 minus that, so these numbers have to add up to 100, so 0.19, and 400 people were surveyed, so 400 on the bottom. So we type that into our calculator, we get 0.0384, 0.0384. So what we do is we add that onto 81, and we take it away from our 81. And those two answers give us our population proportion, or our 95% confidence interval for the population proportion. So the two answers we get are 0.848 and 0.771, and we're asked this question corrected 2 decimal places. So our confidence interval for P, the population proportion, is the higher number on the left, 0.85, the lower on the left, 0.77. So we can say with 95% confidence from the 81% that originally responded to the survey to say they like the bar, we can say with 95% confidence that between 77% and 85% of people liked the bar, or at least one bar. The next part of this question, you were given these boxes to fill in. Tick always true, sometimes true, or never true. The first one is when forming a confidence interval for fixed n and p, an increased confidence level implies a wider interval. Well, we've seen already multiplying 1.96 by this square root. This is 95%, the 1.96. 68% confidence interval, if we go to our Z-score table, we'd have to look up where there's 16% in each tail. So for 68%, we're looking up a Z-score where there's 16% in each tail, which is actually just 1. We know that's 1 standard deviation, but it's pretty much rounded off to 1. So if I multiplied 1 by this number, this would give me a 68% confidence interval, which will be a smaller margin than that. And similarly with a 99.7% confidence interval, it's going to make this even wider and wider. This number is going to make it bigger and bigger. So we can say that this is definitely always true. Second part of this, and as the value of p-hat increases for fixed n, the estimated standard error increases. Well, we may need to look at 3 here. Let's look at 2 at the lower end. So let's just look, we don't need the 1.96, we're just looking at the standard error. Let's take 0.3, so 30% success, or said yes, or whatever it might be, by 0.7, and let's take 100 as the sample. Let's see what that gives us. Then let's see what 0.4, so p-hat's increasing by 0.6 over the square root of 100 would give us. Now they're both less than 0.5, and I think they will show an increase, but I think if we jump up to a higher end, what about 0.8 by 0.2 over 100? What would that give us? So typing these 3 into your calculator, you're going to get 0.045 for this one. For this one, you're going to get 0.048. So we can say yes, standard error increases. But if we type this one into our calculators, we're going to get 0.04. So actually, it's not always true. We've just proven that. It's definitely never true. Not never true, because we've shown that here. So this one has to be sometimes true. So always within these questions, they don't want you just guessing. They want you doing some sort of maths to show. They're not looking for the work, but you have to do the maths to show the work. You're not going to be able to just guess these things. Part 3 of this question, as the value of p-hat times 1 minus p-hat increases for fixed n, the estimated standard error increases. Well, let's have a look at a couple of calculations here. We should know at this point that the max value for this is 0.5 by 0.5, which is 0.25. Now if we take, say, like 1% at the very end, the very beginning, 0.99, now that would give us 0.0099. So it's a tiny number. It's going to increase from here to here. So what about 0.4 by 0.6? Well, you can see that's going to be 0.24. So this value is increasing from here to 0.24 and increasing again up to 0.5 by 0.5. But once we go past 0.5 to 0.5, the symmetry starts taking shape. So in the middle, in the very middle, we're going to have 0.25. To the left of it, it's increasing all the way to the middle, and then it's decreasing all the way back up to what will be the reverse of this, 0.99 by 0.01. So this is always true. As it increases, this increases, but once it starts decreasing, which is not what we're after, as this increases, the estimated standard error also increases. So that's definitely true all the time. And for the last part here, we should be able to see as n increases, the estimated standard error increases. Well, we know that's the opposite. As n increases, the standard error decreases. The bigger the sample size, the more accurate we are, so the error will decrease. So that's never true. We'll have to use calculus to show the max value of this. Well, if we change it into y is equal to x times 1 minus x, we're going to get y is equal to x minus x squared. dy dx, we know to find max, we're going to differentiate, solve for it equal to 0. So 1 minus 2x would be equal to 0. So 2x would be equal to 1. So x would be a half. And then to find my actual max value, I put it back into the original. So I'm going to end up with a half times 1 minus a half, which is a half by a half, which is a quarter. We've kind of touched on this already up here. This max value in the middle, and we kind of showed it here, half by a half. So that's the calculus to show it. But you could leave this p and p if you wanted, or p hat and p hat, but maybe it's easier to change it into x in this case. Part 3, we were asked the largest possible value of the radius. Well, this is just the spread. We looked at it earlier. We had a plus 1.96 plus and minus. So that's what we're looking at here. The biggest spread, they call it the radius in this question to confuse you. The largest possible value of the radius of a 95% confidence interval for a population proportion given a random sample size of 800. Okay, well, it's going to be 1.96. We've worked out our max value. It's when it's 0.5 by 0.5. And we type this into our calculators. We're going to get 0.0346. 0.0346. And you can see that would go from here. We have p here. It would go up 0.0346 and back 0.0346. So the radius, this would be a diameter, so the radius is just one of them, which is the value we just got. We could write as 3.46%, but either one was fully correct. The last part of this question, financial maths question. When the employee retires, they're going to get paid $20,000 on the day of retirement. So that's the first term of a sequence. We should set that up. So A is equal to 20,000. So what's happening? We're going to get 1% more. So the next year we're going to get 20,000 by 1.01. But we have to apply our AER, just 1.024. So the present value of that will be less. And that's going to go on continuously for another 25 years. So this one will be to the power of 1. The next payment will be 20,000, or what we'd have to put away now today to get this payment in 2 years' time. 1.01 squared over 1.024, all the way to the last payment, which will be 20,000 by 1.01 to the power of 25 over 1.024. Now be careful here, it's the next 25 years, so n is 26. So we're able to put this into the formula for the sum of n payments. Sum of n payments of a geometric series is a times 1 minus r to the power of n over 1 minus r. So we have a is definitely, put an extra 0 in there, so 2,000, 20,000, and then what do I multiply 20,000 by to get this? Well, I got to multiply by 1.01 on top and 1.024 on the bottom. So this is my common ratio. So this is just calculator use when you know how to set it up. 20,000 by 1 minus 1.01 over 1.024 to the power of 26, because it's 26 payments, be careful, over 1 minus or 1 minus 1.01 over 1.024. It's easy to go wrong typing this into your calculator, so I would suggest always do it twice. So let's see what we get with this. So checking it twice in the calculator, I get 440.4015, and I don't think they ask us to round this off, so just 440132.40 would need to be set aside for the person's retirement fund on the day of retirement.